Welcome to the fourth workshop on proximity perception. Today we will have, in this session, we will have two speakers. One is Professor Zackory Erickson from Carnegie Mellon University and Professor Lorenzo Jamone. And first we start with Zackory Erickson, and Stefan, you will give the introduction.
Right.
Oops, sorry.
Yeah. So thanks for the introduction, Yitao. So it's really my pleasure to introduce our next speaker, Zackory Erickson. So Zackory received his PhD in robotics at Georgia Tech and was advised by Professor Charlie Kemp. He is now currently starting his position as a tenure-track assistant professor in the Robotics Institute at Carnegie Mellon University, whereas he's leading the Robotics Caregiving and Human Interaction Lab. His research explores intelligent physical human-robot interaction with applications in healthcare robotics. So I'm very, very pleased that we can have him on our workshop, as I think that healthcare robotics is a very interesting domain for the deployment of proximity sensors. And yeah, I'm really curious to hear what you have to say and what you have to tell about your experience in this domain. So please you start your presentation.
Thank you, Stefan. I'll share slides here. So one thing is Stefan and I have actually been kind of in communication for many years now, and sadly we keep meeting virtually, but we haven't met in person yet. We always miss each other at conferences, so hopefully that'll change in the future.
Yes,
but not this year.
Not this year. Yeah, no, but yeah, at least we get to meet over Zoom, and yeah.
Yep. Yeah. So thank you for the introduction. That was all right. So hello everyone. I'm Zackory Erickson. As Stefan had mentioned, I'm an assistant professor in the Robotics Institute at Carnegie Mellon University, and I'm starting there this fall. So within this coming week, I'm kind of getting started and building up the lab. So I'll be leading the Robotic Caregiving and Human Interaction Lab at CMU. And today I'd like to share with you some of our work on developing capacitive servoing for physically assisted robotics. So my research focuses predominantly on intelligent physical human-robot interaction, where robots are in close physical contact with people. Robots that are touching a person, applying force, sensing, and manipulating both the human body and objects around people. And when physically interacting with a person, it's crucial for robots to sense where a person's body is and to track human motion in real time, whether that be tracking a person's face during feeding assistance, sensing and adapting to limb motion, giving dressing assistance when helping someone dress different garments, or navigating the contours of the human body during bathing and hygiene assistance. Now, there's a couple different methods that robots have used to sense human pose in the past. Probably one of the most common ones that we're most familiar with is visual perception, such as with a camera. For example, you might be familiar with tools like open pose. However, different objects or things like the robot's own body and different objects like fabric garments can all visually occlude sight of a person and kind of create these occlusions. Another approach is force perception, where a robot is using its sense of touch or a force torque sensor in order to sense where a person's body is at. But this requires robots to be continuously making contact and applying force under a person in order to sense where their body is at. And more recently, my colleagues and other research groups have demonstrated how robots can use a pressure mat on a bed in order to estimate a person's pose, as well as kind of approximate geometries of their body, including their gender. Yet such approaches like this struggle with estimating local pose details or tracking human motion in real time. But I really want to emphasize, why can't we just use a camera on a robot? It seems like the most intuitive thing to try first. And it turns out that there's a lot of scenarios where in physical interaction, where substantial parts of the human body become visually occluded. In this case, right here, about halfway through this dressing scenario where a robot is helping pull on this sleeve of a hospital gown onto a person's arm, the robot is no longer able to see the person's body here. right? Not only is the robot's own arm getting in the way of its cameras, this fabric garment is also visually occluding sight of the person. So if the person is moving around underneath this cloth, the robot isn't going to be able to visually see that. And this lack of vision is one of the major challenges that capacitive sensing, what I'll talk about in this talk, aims to address. And in fact, in this video, the robot is using capacitive servoing to adapt to any arm movements made by this participant. So what I'd like to share with you is how we've developed new capacitive sensors that can be used to accurately sense local human pose near a robot's end effector. We use learning to build pose estimation models from capacitance data, and then we evaluate through human studies how robots can use the sensor to perform servoing around the human body and adapt to human motion during physical assistance. But first, what is a capacitive sensor and how does it work? Well, you might be familiar with the classic physics definition of a parallel plate capacitor, where we have two parallel conductive plates. One is a sensor, the other one acts as a conductive ground plate. And given this setup, we can use a common capacitance equation in order to determine the distance between the sensor and ground plate, where we have some constants. K is a dielectric constant, epsilon naught is the permittivity of space, as well as a surface area of the two plates and a capacitance measurement from the sensor, which is C. And it turns out we can use this exact same approach to sense the human body. We again have a conductive sensing plate, but now the human body becomes the ground. And we can use similar techniques and equations in order to determine the distance to a person's body. And you're probably actually very familiar with capacitive sensing. You might even use it every single day. Touchscreens on consumer devices use capacitive sensing to detect when they make contact with the screen. So capacitive sensors are common within consumer devices, such as touchscreens, virtual reality controllers, and wearable devices. Within human-robot interaction, capacitive sensors have frequently been used as a form of proximity sensing to avoid collisions with people and various objects. Prior research has also shown how capacitive sensing can be used during object manipulation to perform servoing around stationary objects, or to do what's kind of called pre-shaping of an object before grasping it. So before manipulation, shaping to the orientation and size of an object. However, in comparison to prior work, we explore capacitive sensing for physical robotic assistance, including servoing around the contours of human limbs and tracking human limb motion in real time. So when compared to other pose estimation approaches, capacitive sensing is offering robots a number of benefits. It allows robots to sense through some visually opaque materials, such as clothing and wet cloth. It doesn't require robots to make contact with people in order to sense them. And it also allows robots to track human motion in real time. So to start, we developed a single axis capacitive sensor, which can be either held or in this case mounted to a robotics end effector. Shown here, this is a PR2's end effector. And then we explore how a robot could use this sensor to estimate the vertical distance to a person's body in real time when providing assistance, such as dressing on the sleeve of a hospital gown. And with this sensor, we collected data from a single human participant as the PR2 robot moved the capacitive sensor downwards towards a person's hand. And we can plot all the data collected here, kind of shown in this plot, distance versus capacitance. And in order to estimate distance from a capacitance measurement, we used a nonlinear least squares optimization method to fit a function to this data, a function that's inspired by the capacitance equation for a parallel plate capacitor. And so this gives us a very simple and fast function for estimating the vertical distance from a robot's end effector to a person's limb. We then conducted a study with 10 able-bodied human participants in which the robot used this capacitive sensing technique to sense and adapt to vertical arm motions made by participants while dressing on two different garments, both a hospital gown and, in this video shown above here, a long sleeve sweater. And this even works if participants are wearing a long sleeve non-conductive cotton clothing. Despite this unscripted human motion, the robot's end effector is able to stay within approximately 5 centimeters above each participant's arm, and capacitive sensing is allowing the robot to track human motion in real time, kind of regardless of visual occlusions. Another neat aspect of this approach is that it allows robots to follow the contours of a person's body. So in this case here, if we ask participants to hold their arms out and hold steady, the robot can traverse a path along the surface of the limb. The blue line and shading that we see in this figure illustrates the mean and standard deviation of the robot's movements from our trials across all of the 10 participants, where the robot's end effector tries to stay 5 centimeters above a participant's arm. And in more recent work, we've demonstrated this capacitive sensing technique for providing dressing assistance to individuals with physical disabilities. This same model optimized for a single able-bodied participant generalized to people with disabilities. And in this case here, the robot is using a capacitive sensor to adapt dressing trajectories that it has learned in simulation. Capacitive sensing is allowing the robot to adapt to the involuntary vertical motions made by this participant with cerebral palsy while dressing both sleeves of a hospital gown here. But there is a limitation to this method. This single axis sensor only senses the vertical distance between the sensor and a person's limb. It's not able to sense other types of motions or distances, such as this lateral distance, where a person's arm is no longer directly underneath the sensor, nor is it able to sense the orientation of a person's limb in space. So how can we estimate this kind of human motion during physical human-robot interaction? We do so by developing a multi-dimensional capacitive sensor. And this sensor consists of a 3x2 grid of copper capacitive electrodes, which are connected to an Arduino microcontroller board. And these electrodes emit an electric field, which in turn allows the robot to sense conductive objects, such as the human body. And now with this new multi-electrode capacitive sensor, the robot can again sense the human body from about 10 to 15 centimeters away. We can sample capacitance measurements at frequencies over 100 hertz, which allows us to kind of real-time sampling and adaptation. Yet the most important aspect here is that we're able to sense four-dimensional relative pose or position and orientation of a human limb. But what do I mean by sensing four-dimensional pose? Well, here's a PR2 robot again, and in the center is that capacitive sensor. And if we zoom in, what we're going to be looking at is a point on the person's limb that's closest to the center of that capacitive sensor. So now, given this point, let's look at what is this relative pose that a robot is sensing? What are these four dimensions? Well, the first two dimensions are going to be this lateral and vertical distance between the capacitive sensor and the highest nearby point on a person's limb. The third dimension is going to be this pitch orientation between the sensor and now an axis running along the surface of a person's limb. And then the last dimension is this yaw orientation now between the sensor and the central axis of the limb. And together, this represents the four-dimensional pose of a person's limb that a robot is going to be sensing. And if you're wondering why this isn't 6 dimensions, it's because of the ambiguity along a central axis of a cylindrically shaped limb. Now, in order for a robot to perform capacitive servoing around the human body, we start by collecting time-varying capacitance measurements from a single human participant as the PR2 moves the capacitive sensor around both the person's arm and leg, shown in this video here. We feed all the data collected from this process into and train a fully connected feed-forward neural network, which takes as input at every given time step a window of prior capacitance measurements observed from this sensor. And then this network outputs for us an estimated pose of the person's limb at a given time step. And again, note that this model is trained on only capacitance data from a single human participant. So to train to control a robot to perform servoing around the human body, we use a PD controller, a proportional derivative controller, to update the robot's target end effective pose. This is a fairly straightforward controller, so I'm not going to dive into the details of how it works. But I will note that one of the benefits of using a capacitive sensor is that it enables robots to perform complex assistive tasks like helping someone get dressed or cleaning off their body with very simple control algorithms. We then set up a study with 12 able-bodied participants to evaluate sensing ranges, generalization, and servoing using our 6-electrode capacitive sensor, which is mounted onto a PR2's end effector. And we begin by characterizing the sensing ranges of this capacitive sensor and trained pose estimator. And to do this, we first computed the pose estimation error as the PR2 moved the capacitive sensor away from each participant's stationary arm, kind of shown in that video on the left there. And this figure on the left now depicts the semicircular planar region of possible end effector positions. And this resulted in the error plot on the right, where here, dark blue is low estimation error from our trained model, and then green is high error. And the capacitive sensor is working best when the center of the sensor is at most 15 centimeters from a person's arm, where the mean pose estimation error within this region is 1.5 centimeters. And we similarly characterize rotational sensing ranges and observe that this capacitive sensing approach is most accurate when the sensor is oriented at most 30 degrees from the human limb. So, as discussed a few slides ago, we trained our pose estimation model on capacitance data from only a single human participant. Now, in order to evaluate this model, we then repeated the training data collection process with all 12 participants. And this essentially forms for us a test set. And we then computed the pose estimation error from our model. And although our pose estimation model was trained on capacitance data from only a single human participant, this model exhibited on average less than 2.5 centimeters of pose estimation error and less than 10 degrees of orientation error per axis across all of the 12 participants in that test set. And we also investigate the benefit of training capacitive pose estimation models on data from more than one human participant using a technique called leave one participant out cross-validation. So the way this works is that we retrain the pose estimation network on capacitance measurements from 11 participants and compute the pose estimation error on data from a single held out participant. We then kind of loop and repeat this process, holding out each of the 12 participants and take an average over all of the results from that process. The table kind of below shows the average error over all 12 training test sets. But the main takeaway here is that the two tables we just saw are actually quite similar. Regardless of whether we're training on capacitance data from only a single person or from 11 people, we observed similar pose estimation performance with less than 0.5 centimeter of difference in pose estimation error and less than 1 degree of difference in rotational estimation error. And these results indicate that pose estimation models trained on capacitance measurements from only a single human participant may likely generalize to a larger population of people. So as a part of this work, we also presented a servoing algorithm for a robot to control its end effector both proximally and distally along a human limb using a capacitive sensor, kind of as shown in the video on the left here. And throughout our trials with participants, capacitive servoing was able to keep the robot's end effector on average within 1 centimeter from a target distance away from a human arm, while simultaneously traversing along the arm kind of around a bent elbow. And we also evaluated the case where the robot navigates along a human leg. Again, the capacitive servoing kept the robot's end effector on average within 1 centimeter from a target distance away from the top of a human leg. And this enabled the robot to kind of traverse its end effector from the thigh of a person all the way down to their ankle around a bent knee. We then conducted a separate study with 4 able-bodied participants in which we had to provide assistance for 2 different activities of daily living. The first one we've already seen before, dressing, pulling on the sleeve of a hospital gown onto a person's arm. But the second task is now bathing assistance, in which the robot is using a wet washcloth in order to clean off a person's arm or leg. So when providing dressing assistance, we observed that the robot was able to use capacitive servoing to sense and adapt to human motion, such as these lateral arm movements and rotations that we see in this video here. Despite kind of this unscripted human motion, robots are able to, this robot here, the PR2, is able to sense and adapt to that motion. And in the next part of our experiments, we assessed how the robot can use this same approach to assist with another task, bathing assistance, where here the robot is using capacitive servoing along with a wet washcloth So a wet washcloth is placed over these sensors, and this allows the robot to navigate and clean off the surface of a person's leg. And overall, we find that this approach, it works well, but it isn't perfect. Sensing the human limb through wet cloth is which the robot failed to fully clean off the leg. It briefly lost track of the knee and missed some of the blue powder near the knee, resulting in a failure case here. And similarly, we also look at bathing assistance along the human arm. Despite only being trained on a single human participant and with limited training data, capacitive servoing was still able to generalize across multiple people with varying sized limbs. And generally, this type of sensory modality is ultimately working towards the development of intelligent robotic caregivers in healthcare. My goal of bringing robotic caregivers into real environments to assist and interact with real people who require daily care and physical assistance with activities of daily living or self-care tasks. And so overall, capacitive servoing is a new technique that enables robots to both follow trajectories along the body and track human motion in real time. We've developed new capacitive sensors for robots to accurately sense the human body. We've trained pose estimation models based on capacitance data from these sensors. And then we've performed evaluations through human studies in which we found that this servoing approach generalizes well across people for multiple physical assistance tasks, including both dressing and bathing assistance. And so with that, thank you. It's been a joy sharing this research with you all, and I'd be happy to take any questions now.
Thank you, Zackory, for this very, very interesting talk. Yeah, a small round of applause. Yeah, so actually, I will get ahead of the other people and ask a question myself. And,
go for it.
So one of the things I found interesting about your research is your intensive study with with users and end users. And I was wondering, do you have any future perspectives on this? So in terms of application, so you showed dressing and washing, but have you thought about maybe handover tasks? Is this something that is on your horizon? So I guess it's also a kind of essential capability, skill in assisted living. So that would be my question. What is your future perspective on what kind of studies would be interesting?
Yeah, this is a good point. I think some of my colleagues here have some potentially good insight on this as well, looking at things like in manufacturing scenarios, kind of or collaborative industrial settings, physical human-robot interaction, and other types of applications. There's definitely avenues within that. Several other people have looked at these kind of cases. One thing you had mentioned is kind of object handovers. That definitely seems within scope. Kind of, can we attach these capacitive sensors of various types onto your robot's end effector and allow that to kind of sense when a robot is getting close to people as a mode of looking at, well, when is a person near the robot? When is it potentially ready to kind of take this, kind of perform that transfer? That's definitely within scope. There's even within the assistive domain, there's I think a lot of different types of tasks that people in general need assistance with, either due to older age, it could be due to disabilities, either disease or impairments not disease related. And so there's a lot of different types of tasks, for example, feeding assistance. And could we, this is one that I think would be potentially interesting, is different types of sensors, either a sensorized spoon or potentially just sensors on the robot's end effector that can kind of project a large enough electric field that it can sense past a spoon. And robots can also use that to kind of detect, is it getting close to someone's mouth? Have they done any quick motions recently that might, again, once you get close to a person's face, you might start losing some of that visual observation of what a person is doing, kind of like local movements. And so it can help kind of realign a spoon to a person's mouth if they happen to do any small adjustments. And there's a lot of other types of assistive tasks. That's just a single one. But I would say in general, there's a lot of different scenarios. And I think the big question is, how do you integrate these types of sensors onto a robot or onto different tools to interact with people? That's probably the biggest question. I think there's a lot of different types of applications in which they can be used, and they have been used even in commercial devices.
Yeah, maybe I can just make a small remark about the sensorized spoon. Yeah, I think we at some point we also thought about this, that you can use the spoon itself as a sensor, and you can detect eventually proximity or the transition between proximity and contact, and that could potentially help in improving the interaction. And also coming back at something you said, I just was curious to know if you saw in your user studies that the users felt comfortable with this technology. So did you see that maybe knowing that the robot didn't need to enter in a touch interaction to be able to detect the user was advantageous? Did you see any?
Yeah. So let me, I think screen sharing is still working. Yeah. So absolutely. Some of those responses differ depending on whether it's someone with disabilities versus someone that's able-bodied, that doesn't have disabilities and it doesn't directly need robotic assistance. So I think that the strongest answer to this is some of our studies with people with disabilities. This is one example where we had robots kind of interacting with people that do actually require assistance with dressing in their daily lives. Oftentimes that's currently provided by a human caregiver. And in these kind of studies, at least capacitive sensing in these types of studies were really, we found pretty much necessary. For example, some of the participants that we were interacting with, they had broad capabilities of moving their bodies, but in terms of like holding their body still and such, there was a lot of kind of what might be known as tremors, but essentially involuntary motions that these participants made. And again, once you start dressing, you can't see these types of they're sometimes subtle, but I mean, we're talking 5 to 10 centimeters of movement sometimes, right? Where you're essentially, if the robot's not able to adapt to this quickly, you're essentially just talking about a person just continuously smacking into the robot, right? And they're not doing this voluntarily. It's not like they intend to do this. It's just part of the disability. Yeah. And so in these cases, that would probably be the strongest kind of support that we had found for this type of sensing, is that we really didn't find an alternative way. Like this sensor really, it was crucial in order to kind of adapt to this motion so that people weren't smacking against the robot, so that the cloth was able to kind of adapt to motion. Same thing, like they lower their arms halfway and during the dressing process, the robot can still sense that and adapt accordingly. Right? And even in cases with able-bodied participants, it's not as strong of like a clear message where they say like, oh, this is really great and I would definitely want to use this, right? Because it's a little bit different in those cases. It's more focused on evaluating the technical contributions of the work and actually how well does the sensor perform, rather than kind of the real world impact of it. But even in those cases, that's really those kind of cases with able-bodied participants, that's really start to kind of investigate how much can these sensors adapt to in terms of human motions, right? How quickly can they adapt, and how like magnitude and speed of adaptation to different types of motions, and then following different contours of the body, bending around elbow joints and such.
Thanks, Zackory. I actually am very interested in continuing this discussion, but I'll leave the other participants to ask questions as well. And yeah, so I didn't know which one was first. I think it was Christian or Hubert.
Right. So thanks, Zackory, for this nice talk. I have to say, that's really a great achievement, that you can show that you can use capacitive sensors and you can train a system which is then in the end able to assist a human. So I think this is really pushing forward the whole topic of proximity perception. It's really nice to see. I'm wondering, maybe comment on, let's say, current limitations this system has, and what is, let's say, your conclusion out of this, and how would you continue? And for example, thinking of other types of sensors,
fusing them with capacitive sensors. Do you have any ideas on that and some specific approaches in mind?
Yeah. So there's kind of two parts of there. One is like, what is the limitations, and then what is like multimodal sensing opportunities. From a limitations perspective, there's one I kind of already noted, which is that, I mean, if you're working, some types of objects are conductive and do interfere with capacity, like the electric fields that are emitted from a capacitive sensor. Obviously, many of us know this well. Wet cloth happens to be one of those. And so like in this case, using wet cloth it doesn't prevent capacitive sensors from working. It just significantly reduces the range upon which they can sense other conductive objects through it, right? So sense the human body through wet cloth. So that's one clear kind of limitation or avenue for improvement, maybe. There's also, I mean, I think a very clear limitation is that it's very difficult to both have lots of sensors and have them small enough that you can kind of, there's this weird scenario where you want lots of sensors and you want them to be small, but you also want to sense really far away from the robot, right? And that combination doesn't actually really work out that well. In order to get really long kind of, maybe I have a better figure for this. In order to really sense the human body from a long distance away, one of the ways in which you do this is you maximize the surface area. And that means that you're needing a lot of like surface area on these conductive sensing elements in order to sense. If you want to sense more than 5 or 10 centimeters away, you need a lot of surface area. So you're pretty much covering the whole robot in a single sensor, right? Whereas if you want to have lots of different types of sensors, this becomes a challenge of how do you, so there's kind of like this fine balance between the size of the capacitive electrodes and the distance upon which you can sense. So that's I would say another kind of current limitation is that if you want to have a lot of different sensors to kind of, you can almost think of this as like a bunch of different sensors, like pretty much proximity sensors, and using this to kind of build like a proximity map of like different objects near this sensor, right? The more sensors you have, the kind of higher resolution proximity map that you could build, but there's that limitation of, well, the more sensors you have in a smaller surface area, the less distance typically you can sense.
I think
so that would be, I would say, another major challenge.
Just a small remark that I think we are also interested in this subject, and there were some ideas of using like a dynamic spatial resolution where you short circuit some sensing elements so they become a larger electrode, so you increase the sensing range, and if you're closer, you can increase the spatial resolution. Yeah, it's not as, it doesn't work as nicely as it sounds, but it's at least an idea that can be promising. So
no, I really like this. Yeah. I mean, you also have to deal with like the challenges of like electromagnetic interference, and we have like all these different electrodes connected together or potentially overlaid and such. But I do kind of like that idea of, can you essentially like have an on-off switch, or kind of essentially a switch that's connecting or disconnecting different electrodes. You can go from high resolution to low resolution, and you can kind of in real time or approximately change how far away the robot can sense versus its resolution in that sensing range.
Yeah,
I really like that.
I can definitely give you some hints on this.
Yeah, that would be neat. Happy to talk afterwards.
Great. Okay. Yeah. Okay. And next question.
Yes, thank you for the presentation. Actually, it's really nice that the sensors here can be used such for this assistive task, basically for the human. What I did not fully understand was basically the serving with the wet cloth. So what was the aim here? So you still wanted to have some distance, or how was that meant?
Oh, so we're talking wet cloth servoing this one?
Yes, because it should be in contact here, shouldn't it?
Yes, so contact is important. So there's a couple different elements. So first is, I would say, in some scenarios, you can actually do this with just a force torque sensor. If you have some form of like effort sensing or force torque sensing, you could do this without capacitive sensing. What I think capacitive sensing really comes into play here is particularly having multiple electrodes, is it allows robots to essentially follow the path of a person's limb, right? So if you, if for example, you could imagine like crossing your legs, right? Where it's not just a linear path here. You actually, even in here, there's a bend in the knee. So the robot's actually having to rotate around the knee if we kind of play this. And that's one of those elements that capacitive sensing comes into play, is that you have an array of electrodes. And once you start getting past the knee, some of those electrodes are sensing, oh, we're now shifting and we need to rotate around a knee here. So that's one element that capacitive sensing helps with. And of course, if you start looking at different types of geometries or shapes, bends of elbows, then that allows, capacitive sensing allows a robot to sense when it needs to traverse around an elbow. And again, if a person is moving during this process, so if a person drops down, capacitive sensing could sense that as well. So kind of, I would say that those are some of the key benefits of it from like a bathing assistance, is it handles both maintaining contact, but also kind of adapting and following the contours of a person's limb.
So, but the essentially had the 6 electrodes, and so more or less the outer ones were for proximity, and you maintain the distance for these outer ones, or because I assume that the middle one was in contact, basically, just with the wet cloths in between.
Yeah, so this is where there's probably a few details I actually missed here in explaining this. But essentially the robot is being told keep the end effector within like half a centimeter from the arm, essentially the thickness of the cloth, and then keep the sensor centered along the central axis of the limb. And so essentially keeping the center 2 electrodes in the middle of the person's limb as it's traversing along the limb. So there's a couple of details in the controller of how this works. Essentially, the only difference between dressing and bathing assistance is telling the robot a target. Instead of staying like 5 centimeters above a person's limb, you're now making contact with the limb. And that's really pretty much the only difference between these 2 scenarios, is the target upon which the controller tries to keep the end effector.
Nevertheless, the wet cloth, basically, it's also quite conductive at the end, and more or less, you should only measure the distance to the wet cloth. So why can you measure here through this one? Can you say maybe something about the frequency that you have been using here, the measurement frequency?
Yeah, so in terms of the wet cloth, it doesn't actually entirely get rid of so if you were to maybe put a metal plate in between the sensors and a person's arm, that might entirely ground all of the electric field. But a wet cloth doesn't entirely ground all of the electric field. So we're still able to sense the human body about a centimeter or so past the wet cloth. And that's really what allows these sensors to work, is so that when they get to, for example, an elbow here, some of these sensors, particularly like on the corners, they're starting to sense, oh, I'm getting close to the elbow. This sensor is no longer has as strong of a signal, and so I need to start rotating the sensor accordingly. And so part of it is, I would say, I think I agree with you, is that definitely the wet cloth is hampering the electric field and the distance upon which we can sense, but it's not completely negating the electric field. We can still sense the human body from essentially a shorter distance away. So the same approach that we're using for dressing assistance works here. It's just can't sense as far away, but that's okay because we're making contact. So if contact stops happening, for example, we start going off of the limb or the person's arm moves, the robot can still sense that and adapt accordingly.
Yeah, never tried it, so I would have assumed that it really gets difficult. But
we also thought about this. We also assumed it wouldn't work until we kind of tried it, and it's like, oh no, it does work. It works okay. It's not perfect, right? This is still definitely one of the limitations. Is is kind of this, essentially it's creating more electrical or like electromagnetic interference with this sensor.
Yeah.
Okay.
I think I have, well, I think I have some ideas about this, but I might suggest that we can just make an appointment for another meeting, and we can continue exchanging the ideas so that we so we progress with a session. Just I was interested still in hearing Matt's question, but I ask you please to keep it short so that we can continue with Lorenzo's talk.
Hi, so my research focuses on whole body proximity sensing, and I was wondering if you could. Oh, can you hear me?
Yep, I can hear you.
Oh yeah, so I was wondering if you could comment on like how important do you think whole body sensing could be for assistive robotics? Because I don't work on I myself don't work on specific use cases like this, but I was wondering if you could comment on it. Yeah.
Oh, I like this. So whole body sensing is really nice. So the types of sensors I showed here, they're just local, essentially local proximity sensing. So you don't really get a full picture of what's going on if people are moving their torsos or if someone stands up. You don't sense any of that. And so vision is one approach of getting like whole body sensing, approximate. But in general, within assistive cases and scenarios, there's local sensing is one thing because it's nice to kind of get rid of some of the visual occlusions, and you can get kind of very accurate local details of what's going on right here at the point of contact. But then there's a bigger question of what happens, what are people doing more broadly? And that might result in more extreme kind of local aspects. So for example, if someone stands up, you might still be able to sense someone's arm moving, but you're going to get a lot of arm motion over a very short period of time when someone's standing up, right? And you might be able to adapt to that more quickly if you have a better picture of what someone's doing for their across their entire body. That's just a little bit of insight as like an example, but in general, that's a whole nother kind of aspect of research that's very important in assistive care, in general, sensing the body, both from a global perspective and a local perspective. What I shared here is the local perspective, and what you're talking about, the global perspective, is still very important across the board with interacting with people.
Thank you.
Thank you.
All right, thanks, Zackory again. And yeah, I want to hand over the word to Itao or Christian. I don't know exactly who is going to do the introduction, but please.
Caspar, since you're here, do you want to introduce?
Yep, happy to do that. Sorry I couldn't join earlier. I was in another meeting and that just took a bit longer than expected. But yeah, great to be here just in time to introduce the next speaker. And it gives me really a great pleasure to introduce Lorenzo Jamone. And he is at the same place where I am at Queen Mary, in the Center for Advanced Robotics at Queen Mary, as we call it. And he's a senior lecturer there in robotics. And he's also a Alan Turing Fellow. And he is definitely a leading figure now in cognitive robotics, and more or less in his own words, very keen to build intelligent robots, taking inspiration from humans, and then also to see whether we can validate any theories of human cognition by, trying these things out on robots. And I mean, to me, he is really a leading figure in intelligent manipulation and visio-haptic perception. That's what I see mainly coming from him. And he has been around quite a bit. He has been at the VIS lab at the Instituto de Sistemas et Robotica of the Instituto Superior Técnico. And he has been also at Waseda University at the Sugano lab, and also involved with the Takanashi lab, also at Waseda University. And he was, of course, many years at IIT in Italy. So yeah, quite some expertise in cognitive robotics in particular. And I look forward to seeing what else you can tell us today about your work, Lorenzo. Over to you.
Yeah, thanks, Caspar, and thanks to the previous speaker. Very interesting presentation. I'll share my screen. Share. And all right. Okay, so I hope you can.
Yep, all good.
You can see my screen.
Yep.
Okay, so yeah, thanks everyone, and thanks for inviting me. Caspar, as Caspar already introduced me, my name is Lorenzo Jamone. I'm a senior lecturer at Queen Mary. Today, although indeed I am very interested in cognitive robotics and intelligence in general, today I will focus mostly on tactile sensing for robotic manipulation, and I will introduce one particular kind of tactile sensor based on magnetism. And I had a slide about my background, but I think Caspar covered it already, so thank you for that. The highlight is that since 2016, I joined the Queen Mary University. You may know about the university. We are a Russell Group university, very research active, and we are also proud to be very diverse and inclusive, as many of our students come from Black, Asian, and other minorities. And I'm part of ARC, which is Advanced Robotics at Queen Mary, led by Caspar. We do robotics in a wide sense. We do robot bodies and brains, and we apply them to several applications. You can see some example of the amazing soft robots Caspar does with his team. My team is most focused on manipulation and cognitive robotics. And in fact, we go by the name of CRISP, Cognitive Robotics and Intelligence System for the People. And this is a picture of the team, a PhD student and a postdoc, and myself. And yeah, so within cognitive robotics, what we mainly focus on is what I call the intelligence of our hands, and which relates to the ability we have as humans to grasp and manipulate objects, but also to explore objects haptically and gather information about them, and even using our hands for communications with others. And at Queen Mary, I carry on this research with funding from several funding agencies and companies, and you can see some of the logos around. And in particular, I'm currently working on two projects, which that I will quickly introduce. One is called the MAN-3 project and human-inspired robotic manipulation. And here we try to transfer the intelligence of humans to a robot by demonstration. So the idea is that a human person will demonstrate a robot by teleoperation to do some dexterous manipulation task. And then we can learn the essence of those actions and reproduce it in different contexts. And related to the topic of this workshop, there is a big influence of tactile sensing in this. And of course, when we do it with teleoperation, we are interested in tactile sensing on the robot side, but also in haptic feedback so that the human user can receive the tactile stimulation that the robot is sensing. And another project we are involved in, a different scenario, is in nuclear decommissioning. And here as Queen Mary, we have different people working on this, on a number of different tasks. And again, myself, I'm mainly involved in the aspects of tactile sensing and grasping and manipulation. And yeah, so going more in the topic of this specific talk, I want to talk about tactile sensors and to give some examples how they can be used in robotic manipulation. And as I said, I will talk of a particular kind of tactile sensors that I will now introduce, where the main ingredients are soft materials and magnetism. So if we look at humans, we use tactile sensing for a lot of things. We detect different properties of objects, and of course, tactile sensing is crucial in order to be able to manipulate the object. and, for example, delicate objects without crushing them, but also to understand specific properties of objects, such as their shape or their texture, etc. And we would like to replicate this in robots. And if we think about robots today, the majority of robots that are employed, for example, in industry, but also in other settings, they can still do manipulations, but if they don't have tactile sensing, they will typically manipulate only hard objects. They will do it in structured environment, and they will, most important, they will not gather additional information about the objects while they manipulate them. On the other hand, if we think about robot with a sense of touch, for example, we could manipulate delicate objects. We could do it in more unstructured environments, such as the one depicted in this picture. And we could understand object properties while we manipulate the object. For example, think about a scenario of robotic harvesting in which we can pick a grape, and at the same time, we can delicately handle a grape, but also tell something about the quality of that fruit. So if we look at humans again, we detect, our sense of touch is based on several receptors that we have in the skin. Typically, these are mechanoreceptors. We have different kind of them, and different sensors are good to detect different properties. And in my research, I took, I would say, mild inspiration from two different kind of receptors that are present in the human skin, the Merkel disc and the hair follicle, to develop tactile sensors that are particularly good at detecting specific properties. And so we have these two families of sensors. But as I said, they share the main principle of using soft materials and magnetism. And I will tell you a bit more about how do they work. So this first kind, it's, if you see in the picture, we have a soft material, imagine some silicone or a deformable rubber, with a magnet immersed inside the soft material. And then we have a magnetic sensor below. And in this case, this could be a Hall effect sensor, hopefully a 3D Hall effect sensor that will measure the magnetic field generated by this magnet on the 3 axes. Now, if you apply a force, there is a deformation of the material. The magnet will move with respect to the sensor, and therefore the magnetic field that is measured by this magnetic sensor will change. Now, this can give us an indication of the normal force that is applied. But if we are using a 3D magnetic sensor, we can also measure the shear forces. So we can basically measure the distance in 3D between the magnet and the magnetic sensor. And therefore, this becomes a possibly very small and low-cost 3D force sensor that interestingly shows very high sensitivity. And this is one of the property that I always thought is very important for tactile sensing. It's probably the first property that you want to have in your tactile sensor. And you see some example here in which we are equipping a hand with several of these sensors. So we have a matrix of these 3D sensing elements on the fingertip of this robot. And we can not only manipulate the object delicately, and this is a very light object that you see, and we can manipulate it without crushing it, but also without losing the grip. At the same time, we can say something about it, for example, the shape or maybe the weight. So, for example, if there is a change in the weight, we can detect it. The other family of sensors is inspired by this structure of a cilia. Cilia is present in not just on our skin, but also in many biological systems. And here we have a cilia, so it's a tiny pillar. It is made of a soft material in which we embed magnetic particles. And then on the bottom, we have again a magnetic sensor, in this case, a giant magnetoresistive sensor that can measure the changes in magnetic field. And you can see here some of the measurement coming from this sensor. Now, because of the sensor that we use, but especially also because of the structure of the cilia, this sensor is very good to detect very small forces. And so we can use it to characterize surfaces. In this case, we are scanning a metal sheet with this sensor that is attached to the black robot. and we can see where the grooves are. In another application, we scan fruits, and basically just by a single scan after some training, we can tell whether the fruit is ripe or rotten. So here we extract specific features from the readings of the sensor that are related to the, we call them waviness, roughness. These are related to the interaction between the cilia and the surface of the fruit. And we see that by using simple classifiers, we are very good at detecting, at classifying fruits in whether they are ripe or senescent or rotten. And we've published these sensors in a variety of forms and in different applications. And this is just a quick list of the publication if you want to know more about these sensors. And I will now go into showing you a couple of examples of robotic manipulation done with some of these sensors. And actually, the examples that I will show are not manipulation using only tactile sensing, but they are manipulation using a combination of vision and touch. Because of course, we are not saying here that vision is not useful or not important, but what we are saying is that tactile can add something. And in fact, in the lab, we have done a number of different experiments and with different tasks, where our main aim is to combine vision and touch to try to handle the difficult grasping, let's say. So for example, grasping complex objects with irregular shapes or deformable ones. And at the same time, while we grasp this object, we can say something about the object. For example, we could say whether a part that is grasped by the robot has some defects or not. But the example I'm showing now is of precise pick and place. So when you want to do precise pick and place, of course, you don't want to lose the object that you are picking, but also you want the object to be in the same pose with respect to the gripper when you grip it and when you pick it and when you place it. So this is the example. Let's say we want to pick that object and precisely placing it in the pile. Here, I show that we can detect that there is a slip. So if we detect a slip with the tactile sensor, then we go back, we take another image, and this time there is no slip, and because of that, we can position the object precisely. I'll just show you what the task is. Now we will go in a few details of how did we realize this. So the first thing is the tactile slip detection. And this is actually a paper that is published in IROS this year. So here we did the first data collection. We call it in the wild because there is no specific procedure in a structured environment, but basically we put the object there, and from vision, we realize where the object is, we pick it, we shake it around, and then we put it back. And this is wild data in the sense that the interaction between the object and the tactile sensor can be very different from trial to trial. And you can see we're showing here some events of slips and no slips. And note that some of the slip events do not necessarily cause the object to fall, but the pose of the object in the gripper changes. And that's something we also want to avoid. So we use this data to train some classifiers, and interestingly, even though the data was collected, as I say, in the wild, we can show very good classification accuracy. At the same time, the same data can be used also for object recognition. And I'm not going to show our results for object recognition, but you can quickly see from the tactile signatures of the objects that even if the same object, for example, a tennis ball, is grasped in a different position, there is a similar tactile signature. And so clearly, this can be good data to be used in a classifier for object recognition. Now, in order to program the task that you saw initially, the precise pick and place, I would like to quickly introduce this software framework that one of our students developed. It's called Grip. grasping robot integration and prototyping. And is basically a software framework that allows people to program a robot in a simpler way. And we use this also in collaboration with several companies to realize a number of different tasks. And I will now show a quick video in which Brice, the student who developed the framework, will show you in practice how the task that I showed initially can be programmed with grip.
So here is a gig grip. Let's start with interfacing the robotic system, including the sensors. To do so, we first need to specify the URDF file, which is a description of the robot. Then, instead of using grep to start and run the tactile sensor, we can decide to use the launch file provided by the slip detection method. What remains to be integrated to grep is one robot arm, one end effector, and the Kinect.
So basically, you have a series of graphical user interfaces that allow you to program a robotic task just visually or adding some numerical information about the different position, but without actually.
Now we can start designing the task by collecting a point cloud from the Kinect and using it to generate autonomously a grasp pose using the integrated component. You can navigate inside the editor and hiding the state configuration area by zooming out. If a grasp pose is generated, plan and move the arm to this point. The gripper now needs to be closed to grasp the object. Note that we use a predefined joint state as input of our server. Now we want to move the arm above the table to test if a slip happens. Run the slip detection that will return the outcome corresponding to the orange socket if no slip is detected within 3 seconds. If that is the case, run the trajectory to place the object, go back to above the table and finishes the task. Now, if a slip is detected, go back to where the object has been picked and releases it. Plan and move the arm outside of the field of view of the Kinect and recollect a point cloud to restart the whole process. We have then created a closed loop system. We just need to connect the last sockets, start the robot, and we can execute the task.
And so you see here again the task I showed before. There is first visualization of depth data to find out where the object is. The grasp appears not to be stable. So we execute the grasp again, and the second time we have a better grasp. We check that there is no slip, and therefore the object can be precisely positioned in the pile. Okay, so this was one example in which we used a gripper, a parallel gripper, and a flat tactile sensor that had a matrix of 3D sensing elements. So a lot of tactile information coming from that kind of sensor. I will show now a different experiment, which is done with the dexterous hand, a multi-finger hand. In this case, we have a different kind of tactile sensor, not based on magnets, but that works similarly. But in this case, the sensor provides the 3D contact force, but only on a single point. And with a sensor that is a bit less sensitive than the one we did. But I will still show this. And maybe later we can comment on how a better sensor could achieve even better performances on this. So this other example of how we can combine vision and touch is the idea to first locate an object and then go and explore haptically by touching the object in different positions. So that and this is important if we want to make absolutely sure, or let's say if we want to maximize the chance that when we lift the object is not going to drop. And this, of course, can be, although the process might be a bit slow, this can be beneficial in situations in which you are handling something dangerous or very delicate, and you really don't want the object to fall. And to do this, we employ something that was the topic of some earlier study we did in simulations a few years ago. And in order to find out the best strategy to perform this haptic exploration, we used something called unscented Bayesian optimization. So in general, Bayesian optimization is a way to optimize a search when you want to find out what is the next best place to explore in order to maximize the amount of information and minimize the number of attempts. Now, the unscented version of this allows you to do the same thing, but in addition to find solutions that are more resilient to noise. In the case of grasping, our search is basically driven by a grasp matrix that at any time that we touch the object, it will tell us, oh, this grasp has a good value of the grasp matrix, or this other grasp has a lower value or a higher value, right? Something like that. If we do this with the unscented Bayesian optimization, we can find grasps that not only have a high value of the grasp metric, but also that are close by to other grasps that also have a high value. In practice, this means that, and if you see the images now on the screen, the safe grasp and the unsafe grasp, the unsafe grasp might be a grasp that is very good. But if you reproduce it and you have a position error of 1 centimeter, is not good anymore. In this case, it's very close to the end of the object, to the border of the object. The safe grasp is a grasp that has a high value of the metric. And if you reproduce it, also assuming that there will be some error, it's still a good grasp. So this is what the unscented Bayesian optimization gives us. And these were experiments that we did only in simulation. More recently, Sami has worked on applying this to our robot. And here we see a similar pipeline in which the object is first detected with depth sensing. The rough position is detected, then there is some exploration, and then the objects are lifted. And here you see two possible outcomes, a stable grasp and an unstable grasp. Of course, there could be also a grasp that completely miss the object or that the object falls. But basically what we show is that we have compared different way of doing this exploration. You see in the plot, unscented Bayesian, which is UBO, normal Bayesian, and a classic uniform exploration of the object. What we show is that with the unscented Bayesian optimization, the probability of success of the grasp, so the probability of then realizing a grasp that doesn't fail, is much higher than in the other two cases. And just a comment on the tactile sensing. In this case, as I said, we are measuring the 3D force on each fingertip on one location. And we use that information in order to compute that grasp metric, which is a force closure grasp metric. Okay, and this concludes my talk. Just to summarize quickly, I have introduced a family of tactile sensors that are based on soft material and magnetism. I think the most interesting characteristic of this kind of sensors, because of the way they're done, is that they are highly sensitive, so we can measure very low forces. And they can be manufactured very small. So ideally, we can then have a distributed a sensor that has multiple of these sensing elements, so that we can have distributed measurements of 3D forces. And then I presented a couple of experiments in which, well, some of them I presented with more details, some of them initially just show a couple of videos. But basically what we can achieve is that we can have delicate and stable grasp at the same time. But in addition, we can collect information about objects. And I think this is something very interesting for the application of tactile sensing to manipulation. Okay, and that's me. Thank you very much for the attention, and feel free to get in touch if you want to know more, and I'm happy to reply to questions now.
Thank you very much for the very nice presentation, and round of applause. Very good, thanks a lot. So do we have any questions? So I cannot see any hands, although suddenly the hands are coming. Good. Okay, I think Hubert was first, and then we go to Stefan.
millisecond. Thank you. Well, thank you for the very interesting talk. Since you're using magnetic sensors here, I expect that you also worked here or tested ferromagnetic materials. Did you see any negative impacts on your sensing performance?
Yeah, thanks for the question. So clearly one, let's say, drawback, or let's say one characteristic of this technology is that because we are measuring magnetic fields, external magnetic fields can impact your measurement, right? And the bad news is that it's very difficult, if not impossible, to shield magnetic fields. You can deviate them by using other magnetic fields, but you cannot really shield them. That's the bad news. The good news is that the influence of external magnetic fields, it's reduced a lot quickly with distance. So typically with our sensor, we do not really see a lot of influence of magnetic fields. Let's say in normal situation, let's say magnetic field generated by the motor of a robot or picking up ferromagnetic objects, we do not really see a lot of influence. Additional thing to say is that if you are in a situation in which you think there could be magnetic fields, or let's say you want to be sure that those do not affect your measurement, you can have a reference sensor for the magnetic field, external one, and then compensate for those magnetic field in your reading. So you can have basically a sensor that is not your tactile sensor, but just a magnetic sensor that will read the magnetic field in the environment and compensate for that in the reading of your sensor. And that's something we attempted in we did a couple of experiments about that, and we see that it's one possible solution. In practice, it did, as I said, external influences were really not that big of an impact.
Okay, thank you.
Thank you. And then over to Stefan.
Yeah, thanks, Lorenzo, for this interesting talk. I really enjoy ideas about tactile sensing in general, and I'm not familiar with magnetic sensing so much, so this is insightful. And I wanted to ask you some kind of technical question about the cilia you presented. So as I understood it, you have the magnetic sensor at the bottom, and then you have embedded some magnetic elements along the cilia. And I was asking myself, why is it necessary to have several of them? Wouldn't one be enough to detect the deflection of the cilia?
Yeah, very good point. Yes, it could be done, and actually that's something we are testing now, even to, let's say, to make sensors that, let's say, that could be manufactured a bit more easily rather than with respect to that one. The advantage of having a magnetic element all along the cilia is that you can be even more sensitive, because the amount of magnetic field very close to the sensor is the one that has the highest, let's say, signal to noise ratio. So with this structure, we can, I mean, after a few experiments with this structure, we can really measure very small contact forces. Better than having the element only on the top of the cilia.
And I was also wondering, so these magnetic elements are permanent magnets, right?
These are actually ferromagnetic material. We mix a PDMS, so a silicon, we mix with ferromagnetic material, and then we put it in we magnetize it inside a big magnetic field. So eventually they become permanent magnet, but the particle initially, they are ferromagnetic material.
Okay, so I'm asking
all together in the.
I'm asking because I'm wondering if if it's technically possible to have, instead of the ferromagnetic material, have coils that where you would, you know, maybe use multiplexing, time multiplexing to activate in a pattern sequentially or however fits best. And maybe that could be deliver some interesting movements.
Yeah, that's an excellent point, and we do have a paper about that actually. So yeah, just to mention that this work on this magnetic-based tactile sensing is something that I've worked for about 10 years and in different places. So in collaboration also with Waseda University in Japan and Instituto Superior Técnico in Portugal, and then several students, they they branched out with parallel projects, and one of them was indeed using coils, which basically you can have a generate different magnetic fields, and yeah, it's very interesting.
Great. Yeah, thanks.
Thank you. And over to Shinichi.
Yeah, thank you. Thank you for a nice talk. So I have also one question on the Celia sensor. So how much fine texture so can the sensors detect?
Sorry, can you say it again?
Yeah. So how much how much fine texture? So the Celia can detect the texture, right? So
yeah.
How much fine so the texture so can the sensor detect?
Yeah, to be honest, I cannot give you really a quantitative answer, although we made some tests, for example, with the different type of paper that, they have, let's say, a quantified texture, like roughness of the texture.
Yes,
we did some experiment on that, and we see that we can recognize, for example, different type of papers. On top of my head, I would not know how to better quantify, but
okay.
Yeah, but for example, yeah, I think it was also interesting that we could see the difference in texture of two apples that were of different kind of.
So another question is how does surface condition, for example, wet or dry, so the conditions affect us
Well, that's an interesting point. I think. I mean, of course, for the sensor is measuring the contact force. So for the sensor to be effective at measuring a texture, there should be some friction in between the sensor and the object. So we didn't really test it, but I can expect that if the surface is very slippery, the sensor will just slip and not see a texture. But yeah.
Okay, thank you very much.
Yeah, thank you.
Yep. Okay, thank you. Over to Zackory.
Thanks, Lorenzo. One thing I really liked was kind of like that sensing, the food ripe sensing method that you had put together there. And one question I had, actually kind of maybe two questions. One of them, is it using magnetism to do that? And then the second one is kind of like, what is the response time or sensing time so you're seeing for that?
Okay, so the principle is still using the magnetism. So the cilia itself has the magnets inside and then the magnetic sensor. So the sensor is using magnetism as a sensing principle. What we are measuring is basically are the deflections of the cilia when the cilia is scanning the fruit. And basically there to go a bit more into the details, we go down with the cilia. The first measurement that we take are kind of related to the softness of the fruit, because we push on the fruit and the amount of deflection can be somehow proportional to the softness. Then we move across the surface and we collect, let's say, we collect the deflections, but you can see them also as vibrations, because actually you will see the pattern is some kind of vibration. And then we look at the power spectrum. We extract features that are related to the something similar to the power spectrum of that signal. And that will give us an information about the texture. So basically the roughness of the texture. Then we took them, we put them in a classifier and we classify. There was another question maybe that I missed that I forgot.
Oh, the sensing times.
Sensing time. So the acquisition rate, I think is on the kilohertz.
Yeah,
roughly.
plenty fast.
Yeah, I don't remember on top of my head, but it's kilohertz, I would say.
Great, thank you.
Okay, yeah, thanks also from me. And any other questions?
Maybe if I can ask.
Please.
My question would be, how long can you make this cilia? So right now it's like, I don't know, 1 centimeter, or look like 1 centimeter?
Less.
Yes, okay.
Half a millimeter, 1 millimeter or something.
Okay, so I thought if you could make them longer, for example, 10 centimeters, provide more of them, then you could have some kind of proximity perception. So Similar
Ideally,
like,
yes. So I think, yeah, so I think here yes, thanks. So ideally here our objective was to make something extremely small. That was our focus as well, because then we were thinking possibly integrating this in also different application, different robots. But yeah, the principle can be used also at larger scales. It will still work. Yeah.
I turned my head away for a second, and more questions are coming up. So maybe Hubert first, and Zackory, is that a new hand or an old hand? Okay, so over to Hubert.
Yeah. One question regarding this cilia thing. You said you also worked with rotten fruits or something, and you got some results. So maybe actually it got then in contact with some stuff that remained on the cilia. Did something like this happen? Going further, even did you test basically to clean it if something like this happened?
No, no, it didn't happen. In what I mean is that the fruits that we were examining, they were, well, let's say senescent, maybe is the right word. They were not completely going apart. They were just old, basically. In fact, for the strawberry, so we tried strawberries, for example, and that would have been relatively easy to tell apart also by vision, because all the ones, they are darker. But with apples, for example, the first test we did, we randomly found an apple in the lab after that was there for a long time for some reason. But by looking at it, it will look exactly the same as a fresh one. The texture of the cask instead was different. Slightly different, I would say, but no, it was not like completely rotten. So no, nothing that will stay on the cilia.
Okay.
The cilia is also very delicate, so probably even with the completely rotten fruit, well, I'm not sure how much will stay on the cilia.
Mm-hmm. But you think it's robust enough that you could do some cleaning in such a situation, or?
The cilia?
Yes.
Yeah, they're relatively robust. We are also improving the way in which we fabricate them. The cilia itself is relatively robust. The robustness of the cilia mostly depends on the ratio of soft materials and ferromagnetic particles that you put inside. If you put too many ferromagnetic particles, it becomes less resistant. Mm-hmm. The way we do them now, we have optimized a bit. They are quite robust. Actually, the part that is less robust is the connection, the physical connection between the cilia and the sensor below. But also there we improved a bit. And this is mainly a team in Portugal, in Eschke. They're great with the microelectronics, and they mainly deal with that part. And it's quite robust, actually.
Okay, thanks.
Okay, yeah. Thanks again to Lorenzo, and I pass over to Yitao, is that right, for concluding words?
Right. Thank you everyone for your participation to today's session. I can sense that the panel discussion will be very lively, and with all these nice contributions today. And yeah, as we said before for the speakers, we will, as we said, we will record everything and edit everything for you and upload it to a shared folder. But the speakers, or you have to upload the videos on yourself. So we are not allowed to upload the videos to IROS. Yeah, but we will provide further information via email. And yeah, and thank you for your participation. It was nice to hear all this new information.
Yeah, thanks a lot for organizing and inviting, of course.
Yeah.
Yes, thank you for organizing and hosting this.
All right, then.
Thanks again to the speakers and the audience. All the best.
Bye-bye.
Yeah, thank you. Bye.
Bye, everyone.
Bye.
Bye.